Howdy! This is your friendly neighborhood physics teacher here, and we're going to go over energy, work, power, and thermodynamics. So your test is on Friday. That's Friday, as in this Friday. Friday. Okay, never mind. And just a reminder, you're going to have 14 multiple choice and 5 free response. So the free response are very similar to how your entrance tickets look. So 14 multiple choice, 5 free response. This review will help you understand what's going to be on the test. What Miss Heath did is she looked at the test, she made the review question. Look at the test, we made the review question. Okay, this really does help. This only helps if you actually do the review and just use this video as a check. If you're just copying down the video, it's not going to help you because you can't watch Miss Heath do the test for you and just copy it down. Doesn't work that way. So make sure you kind of at least pause this video right now, try question number 1, and then watch me do question number 1, pause, at least do that for me, please. Okay, and don't forget, after this video, if you have any other questions, please ask Miss Heath and Miss Verona. They really do like having questions, I promise. So let's get this show on the road. So number 1, ice melting into water is increasing in. So if you remember from your mix calculations, we talked about, helps if I write. Okay, we have an ice cube, and it's melting into water. So think about the structure. There's structure here. So not much structure here. Running in a room, not much structure there. So a couple of things to think about. So here is low kinetic energy. It's low entropy. And it's also low particle movement. Because when you have the ice cube, yes, the particles are moving, but they're just basically staying stationary, just sitting there vibrating. That's all they can do. But as ice melts, you're increasing that entropy. So your entropy pretty much goes to medium. Your kinetic energy goes to medium. Your particle movement goes to medium. And if we even take it a step further, and have the water go into oxygen, it increases even more. Your entropy goes to high. Your kinetic movement goes to high. Your particle movement goes to high. Now remember, entropy just means chaos. So lack of structure. So you're going from structure to not much structure to no structure. So you're going from structure, not much structure, to no structure. And as you do that, the particles are able to move more. So since the particles are moving more, you have higher kinetic energy, because kinetic energy is the energy of motion. And then entropy becomes higher because it's not structured. Gas is more chaotic than a solid. There we go. So now let's look at number 2. If 2 small beakers of water One is 70 degrees Celsius and one is 80 degrees Celsius, are emptied into a large beaker, what is the final temperature of the water? Now, remember how energy moves. So you have one beaker that is, make this one 80. You have another beaker that's 70. Which one has the higher temperature? Hopefully, you said the 80. So that means energy is flowing from 80 to 70. So once they get mixed, it kind of evens out. So how much energy would have to move from 80 to 70 to kind of balance out? Hopefully you said like it just needs to move 5 over, right? Move 5, they both become 75. So the mix would be about 75 degrees. Because it's in the middle, kind of balance itself out. Because 5 energy goes to make that warmer. So which beaker from the question above molecules are moving more? So this is asking before they get combined. So again, high temperature is the same thing as high energy. That's why when water is boiling, you actually see that movement because the particles are kind of going crazy. So high temperature means high energy. So the one that has the highest energy is the 80-degree one. So energy transferred as heat always moves from. So how does energy move basically? So if you have a hot object and you have a cold object, you put those two objects together, and they kind of balance out. But the reason why they're balancing out is because the hotter object is moving energy to the colder object. So kind of like what we went up here, so that 80 gave that 70 about 5 things of energy. So it's the same thing. Energy always goes from hot to cold. And remember, in physics, there's no such thing as really cold. It's just lack of heat. So think about it moves from high energy. So it moves from high energy to low energy. Another way to think about it is think about when you're in a very you're in a very busy room. So you're trying to get into tutoring and everyone's in there, or you're just in a very crowded area. You don't necessarily want to be with all those people, right? You want to move where there's less people. Same thing with energy. There's too much energy. They're like, I have no place to move. So it wants to move where there's less energy. Everything wants to be balanced. So next question. So imagine you could observe the individual atoms that make up a piece of matter, and that you observe the motion of the atom becoming more orderly. What can you assume about the system? So now you're becoming more orderly. So think about water becoming an ice cube. So basically, it's freezing. Your water is freezing, so it's becoming more orderly. So a couple of things you can assume is it's going to have, again, that's all that, it's going to have low kinetic energy. It's going to have low entropy. And it's going to have low particle movement. So you are riding your skateboarding to class. You push off the ground and coast. Why do you slow down if energy is conserved? Why do you slow down if energy is conserved? So let's take a look at the skateboard itself. So you have your skateboard. Your skateboard wheels are touching the ground. So we're in real world example. So between the ground and your wheels, there's something called friction. So that friction is what's slowing you down. That friction. Friction, if you like, right now, take your hands, rub it together. Rub. You should be feeling some type of heat eventually. So that friction causes thermo energy to leave the system. So that friction is causing thermal energy to leave. So the reason you're slowing down eventually is because you're losing energy. That energy is going somewhere else. It's not. You are losing energy now. The world isn't. So when you go for like how energy is conserved in the whole entire world, not necessarily in your not in your world, like the whole entire world, the whole entire universe. We're thinking big picture here. So an object can lose energy. I mean, we feel it all. We felt, you felt a little slow. You felt like you've lost some energy. So an object can lose energy, but the whole entire world universe cannot lose the energy. It's just transferred. So when your skateboard slows down, that friction against the ground is causing thermal energy to leave your skateboard. So that's why you slow down. Math problem alert. Okay, a crane can fill a 500 kilogram mass to height, I should say lift, a height of 30 meters in 2 minutes. The work done by the crane is. So let's write down our givens. So givens, need to actually write. So givens. So we're given 500 kilograms, says mass, to height of 30 meters in 2 minutes. So that 500, because it has a kilogram in, because it also said mass, is our M. The 30, which says height, is our Y. And then that 2 minutes is our time. Hold it. Do we like minutes? Hopefully all of y'all are going, no, just screaming at your computers right now. Have people look at you weird. It's okay. But no, we don't like minutes. We need to convert the minutes to seconds. Dun-dun-dun-dun. Oops, there we go. We need to convert the minutes to seconds. So for 1 minute, we have 60 seconds. Minutes cancel, so you do 2 times 60, which you should get 120 seconds. So now our time equals 120 seconds. Whew, there we go. Crisis averted. We're good. We got what we need. So our unknown. What are we looking for? We are looking for work. That is now it's the point in time we figure out what equation to use. Now, we will give you the equations. You don't have to memorize them. We'll give them to you. But it's always good to just know them. So our equation that we need to have mass, we need to have height, we need to have work, right? Because we need work. We need to have work, and we need time. Well, or do we need time? Might be an extra information. We don't know. So hopefully you realize that work equals our change in our potential energy. And so we can do work equals, we can plug in what potential energy is, mass times acceleration due to gravity times height. So we need to add another given, AG equals 9.8 meters per second squared. We plug that in. So we have our mass, which is 500. Gravity is 9.8. Our height is 3 meters. So maybe that 2 was extra information. And you just grab your handy dandy calculator, plug that in, and you get your work to be 147,000 joules. So that crane's doing a lot of work. If we're going to put that into scientific notation, you would move your decimal over 1, 2, 3, 4, 5. So it'd become 1.47 times 10 to the 5th joules. It's a positive because your number originally started be bigger than 1. So that is our answer. Next question. So when doing chin-ups, a physics student lifts her body with a force of 24 newtons, a distance of 0.25 meters in 3 seconds. What is the power delivered by the student's bicep? So let's write down our givens. So what did it give us? It gave us, says a force is 24 newtons. A distance is 2.25 meters in 3 seconds. So F equals 24 newtons. Delta X equals 0.25 meters. And T equals 3 seconds. And it says, what is the power? So we're looking for power. The only power equation we have is power equals work divided by time. But we don't have work. Okay, so now we got to look through all our formulas again, find the formula that will work for work. Work. Okay, never mind. Continue. So W equals our force times our displacement. So basically all you're doing is you're substituting. You're plugging that in for there. So your power equals force times your displacement divided by time. And you can just plug in what you got. Your force is 24. Your displacement is 0.25. And your time is 3. Plug that into your handy dandy little calculator. And you should get your answer to be 2 watts. Think about light bulbs. 2 watts. There we go. So Reveille always runs in with Texas A&M football team. Reveille's mass is 21.3 kilograms, and she can run about 6.7 meters per second. What is her energy during the run? So we're looking for energy. So before we get to it, let's figure out what the problem gave us. So our givens. So it said the mass, so we have mass is 21.3 kilograms. Says she can run at 6.7 meters per second, and we're looking for her energy. So we have mass, we know that's M, 21.3 kilograms. Now, meters per second. So it doesn't exactly tell us what that meters per second is, but it says she can run. So we're going to do V. It is 9 o'clock, people. Should be in bed. So 6.7 meters per second. So that is our velocity. Now, it just says energy. It doesn't state what type of energy, but what energy goes with movement? What energy has velocity in it? Hopefully everyone again is screaming at their computers that it's kinetic energy. So your equation is going to be kinetic energy equals 1/2 mv squared. So you have 1/2 mass times your velocity. Do not forget about the squared. Do not forget about the squared. A few people I was helping with their work, they forgot the squared. And they're like, we're not getting it. You're forgetting the squared. So don't forget the squared. Well, you're not going to forget squared. Yay. Okay, cool. So you plug that into your handy dandy calculator and you get that your kinetic energy is 478.0, we're rounding 8 joules. If we're going to put that into scientific notation, we're going to move it 2 times. 2. And so that'd be 4.78 times 10 to the 2 joules. Da-dun, da-dun. There we go. So Old Rock was getting ready for the game against Alabama by lifting weights. The amount of work, it should be amount, not about, the amount of work he is doing was 245 joules with a mass of 45 kilograms. What speed was Old Rock working at? If you know anything about Texas A&M, anytime they say a story about an old ag, they just use Old Rock. Old Rock did this, Old Rock did that. So a little bit of A&M lore there for you. So let's start with our givens. So it told us that work, it said that work, it is about 245 joules. His mass is about 45 kilograms, and we're looking for speed. So if we're doing our givens, so we know W equals 245 joules. Our mass is 45 kilograms, and our unknown is velocity. So what equation has work, mass, and velocity in it? Hopefully, you're like, oh, work equals your change in kinetic energy. So you can do work equals 1/2 mv squared. Woohoo! So you just plug in what you got. You got 245, 1/2, your 45 mass, v squared. We're going to continue the work over here. So we have 245. You can go ahead and take that 45 and multiply it by 1/2, and you get 2.5 times v squared. Now we need v by itself. So it's being multiplied right here. The opposite of multiply is divide. And what you do to one side, you gotta do to the other. So that cancels out, and you're left with v squared. Again, you plug that into your handy dandy calculator. So 245 divided by 2.5. And that'll get you a 10.89. Yes, I did round. It's okay. Now we need to get rid of that squared. The opposite of squared is a square root. And so you just take the square root of your answer, and you should get about 3.3. meters per second. If I put that into scientific notation, oh look, we don't have to move the decimal at all. So it just becomes 3.30 times 10 to the 0 meters per second. Dun, 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 dun. There we go. Next question. A box pushed with a net force of 200 newtons for a distance of 9 meters. What is the work done on the box? So what's our givens? It says a force of 200 newtons, a distance of 9 meters, and we're looking for work. So givens, we know F is 200 newtons. We know our distance is 9 meters. We are looking for work. So our equation would be work equals force times distance. Plug in what you got. So 200 times 9. Plug that into your handy dandy calculator. And you get 1800 joules. Putting that in scientific notation, you gotta move it 1, 2, 3 times. So it becomes 1.80 times 10 to the third joules. So we have Jack and Jill went up a hill to get a pail of water. Coming down with the pail. Coming down, the pail was 34 kilograms, and they did 453 kilojoules of work. What was the height of the hill? So let's do our, so we have 34 kilograms, and we have 453 kilojoules of work. Let's write down our givens. So it doesn't necessarily say what the 34 kilograms is, but hopefully the kilograms will give you a hint that it is mass, so it's your M. And then it does state that the work is 453 kilojoules. Wait, hold on. Freeze, kilojoules? Do we work with kilojoules? Heck no, we work with just joules. So we need to convert this kilojoules to joules ASAP. ASAP. So look at your metric conversions, see where kilo is, and jump 1, 2, 3. And so you need to move it over 3 times. Or you can sit there and see that your kilo is 3, your joules is a 0 because it's your base. So you're going to move it 3 times. Your decimal's here, so you're going to move it 1, 2, 3. And so your work is 453 joules. There we go. Crisis averted. We're okay. That is a comma, not a period. Awesome. So we got our work, and we got our mass, and we are looking for height. So our unknown is y. So what equation can we use? So now we need equation with work in it, we need equation with y in it. There's only one that will do it, and it is our gravitational potential energy. So work equals MAGY. So we need to add our AG to our givens, which is 9.8. Come back to me. Which is 9.8 meters. Let me write. Meters per second squared. So now we can plug in what we got. We have work, which is 453,000 equals 34 times 9.8, and we're looking for height. So we go over here, so that 453,000 equals do the 34. 34 times 9.8. That gives you 33 point, that's a 3.2y. We need the y by itself. It's being multiplied, so the opposite of multiply is divide. And what you do to one side, you gotta do to the other. So the height of the hill is, drum roll please. It's really big. It's a really big hill. 1,359.54 meters. No wonder Jack cracked his crown. No wonder. We're gonna move it 1, 2, 3 to put it into scientific notation. So it's 1.3. We're rounding 6. 6 times 10 to the 3 meters is our y. And then going to the next one. So Miss Verona went to HEB and was pushing the cart with a certain amount of force. She always knows her force because she never leaves home without her force meter. And distance. She always carries a meter stick with her too. She's just that an awesome of a physics teacher. So what could she make her children solve? Because her children can already do physics. Because again, she's just that amazing of a physics teacher. So think about what she has. So she says she knows her force. So she knows her force. She knows her force. And says that she knows her distance. So for even though we don't have numbers, we can still play the given part. So we know force, we know distance. What could we solve for? Hopefully you're looking through your equations and realizing that work equals force times distance. So we could solve for work. Woohoo! So label the number spots with the type of thermodynamics transfer. So we're looking at 1. 1 and 2 are by the fire. So 1 and 2 are by the fire. So if we're looking at that, so by the fire there are particles moving. So 1 and 2 go with convection, because the heat is making the fire is making all the particles move around it. 3 would be radiation, because it says it's a vacuum. So remember, vacuums mean there's no particles happening. So 3 would be vacuum. 4 would be conduction, because it's touch. So 1 and 2 are the same thing, convection, movement of the particles. 3 would be radiation, because there's no particles in a vacuum, or space, no particles in a vacuum. And 4 would be conduction. So particles, convection. No particles, radiation. Touch, conduction. Things to know. So Wile E. Coyote just ran off a 190-meter tall cliff. He does what cartoons do and hovers there before he looks down. What is his velocity right before Wile E. Coyote hits the ground? So we have height. We have the height of the cliff. And that's about it. And we're looking for velocity. So if we think about our givens were y equals 190 meters. And we are looking for our velocity. Now that will become our initial height, because that's where he starts off. He starts at 190. What would be our final height? Because it's saying right before he hits the ground. So if he's hitting the ground, he's at 0. Because he's hitting the ground. There's no height there. And if he does what cartoons do best and run and kind of pause there and look around, oh no, and start falling with his lovely sign in his hand, so his initial velocity is going to be 0. And we're trying to figure out what velocity it is the final. So remember, anytime you see two heights and 2 velocities, basically anytime something is falling, you are going to have to use Big Bertha. You're just going to have to use Big Bertha. Some of y'all might be saying, what in the world is a Big Bertha? Well, that is our big equation. That is our kinetic energy initial plus potential energy initial equals kinetic energy final, that should be gravitational, plus potential energy gravitational final. Because we have an initial and a final. Anytime you're given 2 different heights, you're going to be working that. So our pulling onto what each equation is, our kinetic energy is 1/2 mv squared, and that is our initial v, plus mag(y), and that is our initial y, equals 1/2 mv squared, that is our final v, plus mag(y), and that is our final y. Now we can just plug in what we got. So 1/2, oh wait, we don't have mass. The world's going to end. I don't know what to do. It's okay. Take a deep breath. We got this. Now, does Wile E. Coyote's mass change while he's falling? No, it doesn't change. So it's okay. You don't need it. Because if we're thinking about mass, so think about math. If I divide that by m, that means I have to divide that by m. That means I have to divide that by m. That means I have to divide that by min. You have to do each little section. Whatever you do to that one little section, you have to do it to each little section. But if we divide m by all things, what happens? That cancels. That cancels. That cancels. That cancels. Just like how energy is conserved, your mass is conserved also. Mass does not change. When this big equation, mass is really not needed because your mass doesn't change. Now, if you're finding your individual kinetic energy and your individual potential energy, mass does matter. But over a whole entire course of an object falling or being thrown up or anything like that, it doesn't matter because it doesn't change. So we can just cancel it out. So that means we're left with 1/2 vi squared plus agi equals 1/2 v final squared plus agi final. So our vi initial is going to be 0 because he's not moving at the top. We have 9.8. His initial height was 190 equals 1/2. Our final, that's what we're looking for. We're seeing how hard he hits the ground, plus 9.8, and our final height was 0 because guess what? He hit the ground. So 1/2 0 squared, that just gives you 0. And then you can plug in your calculator 190 times 9.8, and that gives you a 1862 equals 1/2 v final squared plus 0 times anything gives you a 0. So now we need this v by itself. Since this is being multiplied, you have to divide. That cancels out, so you get your v final squared equals 3,724. Just put it in my handy dandy calculator. Now we need to get rid of that squared. The opposite of squared is square root. Do, 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 do. So you get your phi final to be 61.02 meters per second. For putting that to scientific notation, we got to move it 1 over. So our V final equals 6.10 times 10 to the 1 meters per second. Ba-dum, ba-dum. So next one. Pikachu has a very stretchy face. Charmeleon is being mean to Pikachu by stretching his face 0.1 meters. What is the spring constant of Pikachu's face? So let's do our givens. So it says that he stretches his face 0.1 meters, and we're looking for our spring constant. So our givens, we have so stretches meters, so that's our x, 0.1 meters. And I'm going to do a little quick addendum there because I did not give you the. Dang it. Okay, that's a mess up on Miss Heath. Shame on Miss Heath. Didn't finish the problem. So you're supposed to get that your elastic potential energy of Pikachu's face was about 225 joules. So that's that's a truly hidden given. No, it's really not. That's a mess up on Miss Heath's part. She should have given you that. I will scold her later. So you have x equals 0.1 meters. You should have had your elastic potential energy, and you are looking for your spring constant, which is Newton's meters. So the equation you're going to use is just your elastic potential energy equation, which is 1/2 kx squared. You plug in what you got, 225 equals 1/2. You're looking for k times 0.1 squared. You can go ahead and square your 0.1, and you get 225 equals, and you go ahead and multiply that by 1/2 too. So you get that you have a 0.005 k. And then we need to divide what you do to one side, gotta do the other. So your spring constant of Pikachu's face is 45000 Newton meters. We're putting that to scientific notation, and you're gonna move it a 1, a 2, a 3, a 4. So you're gonna move it 4 times. So your k equals 4.50 times 10 to 4 Newton meters. That is a 4, I promise. Let me try that again. No, erase. 4. Still looks like a 9. Oh well. So Miss Heath is playing Super Nintendo Mario Brothers. She has tried to make Mario run and jump over Bowser while Mario was on a cliff, but her dog, Taz, jumped in her lap, making Mario hit Bowser. If Mario has a mass of 25 kilograms and was running at a speed of 2.5 meters per second off a cliff that was 30 meters tall, what velocity did Mario hit Bowser if Bowser is 6 meters tall? That's a lot of information. So we have that Mario's mass is 25 kilograms. we have that the speed that he's running at was 2.5 meters per second, and we have that the cliff was 30 meters. We are looking for speed, and then we know that Bowser is 6 meters tall. So let's start with our givens. There's a lot of givens. So mass is 25 kilograms. So this is the speed he was running at the beginning, so before he jumped and hit Bowser. So this would be our initial speed. It's 2.5 meters per second. And this is the cliff that he was on before he jumped and hit Bowser, so that our initial height would be 30 meters. We are looking for our final speed because we're trying to figure out how fast he hit Bowser at, and our final height will be 6 meters because that's the height he hit Bowser at. So remember, anytime you see two velocities and two heights, you're going to use Big Bertha. You're going to use our big equation. You're going to use the kinetic energy initial plus potential energy gravitational initial equals kinetic energy final plus, I don't know what shape that was, plus your gravitational potential final. And you plug in your equation. Give me more space. Need the space. Need space. Space. Here we go. And now you plug in all your substitute for the equations. So you should have 1/2 mv initial squared plus mag y initial equals 1/2 mv final squared plus mag y final. Just plug in what you got now. So we have 1/2. We know our mass is 25, and Mario's initial speed was 2.5. Don't forget to square it. We know his mass was 25. Acceleration due to gravity is 9.8. We always assume that things are on Earth, even though I know Mario's on his own little world, but 9.8. And height that he was at was 30. That equals the 1/2, his 25 mass, and that's what we're looking for is our final velocity. Plus, plus mass, which is 25 times 9.8, and the height he hit Bowser at was 6. So you're going to do little sections. So you're going to take your 1/2 times 25 times your 2.5 squared, and you're going to get a 78.125 for that. Plus, you're going to take your 25 times 9.8 times 30, and you're going to get 7,350 equals. You can take your 25 and multiply that by 1/2, and you get 12.5 and your velocity squared. Don't forget your squared. Plus your 25 plus 9.8 times 6, and you get 1,470. Now, we need the V final by itself. So what can we do to this 1,470? It's being added, so the opposite of adding is subtracting. So we're going to subtract 1,470, and what we do to one side, we have to do to the other. So we're going to take our 78.125 plus 7,350 minus 1,470, and you're going to get a 5,958.125 equals our 12.5 V final squared. We need V final by itself. It's being multiplied by 12.5. The opposite of multiply is divide. What we do to one side, we have to do to the other. So that gives us our V, that gives us our V final squared equals, divided by 12.5, that gives us a 476.65. We need to get that squared, so we square root what we do to one side, we got to do to the other. So our V final is 21.83 meters per second. If we're going to put that into our scientific notation, we're going to move it over once. So that equals 2.18 times 10 to the 1 meters per second. And that is our answer. Doo-doo. So next is the roller coaster question. So we have a 100 kilogram roller coaster comes over the first hill at 2 meters per second. Assuming that the roller coaster is frictionless, the height of the first hill is 20 meters. And we want to fill out this chart. And I've given you some hints. So hint, the mechanical energy equals potential energy plus kinetic energy. And then the total energy is the same thing as mechanical energy, and it doesn't change. And if there's a velocity, there is kinetic energy, and vice versa. So a couple of hints. So let's first find out what our potential energy is. So we know that our gravitational potential energy is mass times acceleration due to gravity times height. So if we're looking at the first hill, so we're going to do really? Apparently we're not. Come back here. Okay. So we're just going to do number 1. I'll circle it. There we go. So hill number 1. We can solve for our potential energy. So we know the mass, it's 100. We're on Earth, so it's 9.8. And our height is 20. So we're going to do 100 times 9.8 times 20. And you get a 19,600 joules. So that is our first potential energy. Our second one I'm going to be using that same exact equation. Our mass doesn't change, gravity doesn't change, but our height is 10 meters. And actually, it's not our first hill. I am doing our hill B. Because hill A and the first hill are the same thing. So we're going to label this as A also. So 1 and A are the same thing. Hill B, you're just going to take your 100 times 9.8 times 10, and you get 9,800 joules. So that is your hill B. And then hill C, you'll be using the exact same equation, your potential energy, and you have your mass, you have your gravity, and you have your height. Hopefully you realize that that just equals your potential energy just equals 0 joules. And you can plug that in. Now, I didn't mean to erase that. Now, so you can plug all those. So 1 and A are going to be the same number. B, you have that. C, you have that. So we know our velocity for our first one. So we can look at our first hill. So we're going to do our first hill again. And we can figure out our kinetic energy. Our kinetic energy is 1/2 mv squared. We know our mass. We know our velocity. So you basically just do 1/2 100 times 2 squared, and you get 200 joules. So that is our potential and your for hill 1, and your kinetic for hill A, because it's the same height. Same height, same potential, and same kinetic. So then to solve for our mechanical energy, remember mechanical energy is just your kinetic plus your potential. So you're just going to do 200 plus, what was it? It was 19600. You add those two together, and you just get joules. So that is your mechanical energy. What's so special about your mechanical energy? Because it's your total energy. It doesn't change. It doesn't change. So all of this is the same number. So all of that's the same number. So if we're looking at B, we don't have velocity for kinetic energy. So we can't use the same equation we used for velocity. But what we can do is, since our mechanical energy is the same, we can use this equation, our ME equals KE plus PE. We can use that equation to solve for kinetic energy. Because our mechanical energy is 19800 equals, we're looking for our kinetic energy, plus we know our potential energy, which is 9800. We just get kinetic energy by itself. It's being added. The opposite of adding is subtract. So you get that your kinetic energy equals 1,000 joules. And since you know that your kinetic energy is 1,000 joules, you can now solve for your velocity. I can actually write. So kinetic energy equals 1/2 mv squared. You know your kinetic energy now. We knew our mass. So now we can solve for our velocity. Actually, I'll make this go away. So we have 1,000 equals 50 v squared, divide. So you get 20, square root of 20 is just 4.47 meters per second. Which, if we're looking at the roller coaster, makes sense. So if it's only moving 2 at the top, it makes sense that it's moving faster, because you're dipping down. So then at C, we have zero potential energy. So if our mechanical energy stays the same, and we're using our ME equals KE plus PE equation, our mechanical energy is this. We're looking for our kinetic energy, and our potential energy is 0. That means it's 100% kinetic energy. It has no height. So all of the energy has been officially transformed into kinetic energy. So that should be joules there. And then we're going to do the exact same thing to solve for our velocity here. So RKE equals 1/2 mv squared. Our KE is this all the energy we got, all z and z's. And our mass was 100 v squared, and it's the exact same process. Exact same process to solve for velocity. So you just bring that down, it becomes 50. You divide, so you get v squared. Take that big, huge number, divide it by 50, and then you get 396. We gotta square it. So we get that V equals 19.90 meters per second. And again, that makes sense because we're at our lowest point. So it makes sense that that's the fastest. So there we go. So that is our roller coaster. Now, the only reason that the first hill had a kinetic energy is because it had a velocity. If it says that it's starting from 0, that means it would go from 100 potential energy at the top to 0 kinetic energy to the bottom. But this one had a velocity to deal with. We are almost done. We just got to do our matching. So this is just what's convection, what's conduction, what's radiation. So which process heat transfer through direct contact? Contact would be conduction. Passes through fluid movement, so that's particle movement, that is convection. And then what processes of heat transfer uses electromagnetic waves? No medium, that is radiation. Now we're dealing with our laws. So energy is neither created nor destroyed. Heat loss in one location is gained somewhere else. That would be our, helps if I write. That would be our first law. Total disorder of a system will always increase over time if no energy is input. That would be our second law. When two objects are in contact, heat will flow from high to low temperature until they reach equilibrium. That is our 0th law. And then an absolute 0, or the entropy of the system will be 0. That means no movement. That is our 3rd law. So hopefully that helps. If you have any question, please let Miss Heath or Miss Verona know. And I hope you have a good night. Bye.